Objectives for today. Well, the objectives for this lesson of notes are the ones that are on the board. Describe VSEPR theory and how it applies to a Lewis structure to generate molecular geometry. Describe hybridization theory and apply it to atoms to generate hybrid orbitals. And then explain how polarity affects intramolecular forces. Those are for this whole lesson. Today, I anticipate that we'll just get through VSEPR theory. So really, the first objective is what we're focusing on today. So if by the end of class you feel like you can use VSEPR theory and apply it to a Lewis structure to come up with what the molecular geometry for that atom should be, then you're in good shape. Okay? All right. Understanding which elements bond with each other and how those differences in electronegativity happen only gives you part of the picture. Thus far, we've just talked about which atoms bond with which types of atoms and how changes in or differences in electronegativity cause things to be covalent or ionic, and metallic bonds, we've talked about them a little bit, but that only gives you a partial picture of an atom. The Lewis structures that we draw are great, but they're two-dimensional, and we don't live in a two-dimensional world, so all molecules are three-dimensional, which means that any forces acting inside that molecule, attraction, repulsion, those polarity forces that we talked about with a partial negative and a partial positive charge, those are all happening in 3 dimensions. So it's important to understand what those 3 dimensions look like for each atom we're talking about so that we fully understand the forces that are going on there. Molecular geometry is just defined as the 3-dimensional orientation of atoms around each other in a molecule. Okay. And there are 2 theories that we're going to cover that explain how bonding works in terms of molecular geometry. They are the VSEPR theory and the hybridization theory. Okay. Both of them help us determine molecular geometry. They do it in different ways. Neither one is necessarily better than the other. In fact, if you understand both of them, you'll have a more full picture of what a 3-dimensional molecule might look like. Okay? We're going to start with VSEPR theory. The fundamental part about VSEPR that you should understand is that their theory is that the repulsion between sets of valence electron level electrons that are around an atom causes those sets to be oriented as far apart as possible. So basically they're saying bonded atoms and lone pairs that are around a central atom are going to try and get as far apart from each other as they can while still being bonded to that atom. VSEPR stands for valence shell electron pair repulsion. That's what those letters mean. They're not just a weird name that they gave this. They have a meaning, and I don't think I actually put that in the notes. So feel free to write it down, but I'm not going to quiz you over it. It's valence shell electron pair repulsion. That's what VSEPR stands for. This valence shell electron pair repulsion. This theory accounts for molecular geometry in atoms, okay? And it considers the location of all pairs of electrons surrounding an atom. So not just the pairs that are involved in the bonds, but it also considers the location of lone pairs, okay? Because they still exhibit repulsion forces on other electrons, even if they're not part of the bond. So they will affect the orientation of atoms around each other. So they're going to affect molecular geometry. VSEPR theory simplifies molecular formulas into specific types of atoms, and they use a simplified formula using A to represent the central atom, B to represent any surrounding atoms, and E to represent an unbonded or lone pair of electrons. Okay, so if they were going to do this for methane, which is CH4, they would say that it is an AB4 type of atom. So this is just a type of atom, because obviously methane is not the only molecule that has a central atom with 4 atoms bonded to it, right? There's lots of other ones, but all atoms that fall into this category of AB4, 1 central atom, 4 outer atoms, are going to share molecular geometry. So they simplify types of atoms. And we're going to talk about several different types. I think like 7 of them that are in your chart. Assuming that pairs of electrons spread out as far as they possibly can, the following formulas will have the following molecular geometries. Okay, so this is where your chart comes into play. Don't try to write it all down at once. We're going to go through it one line at a time. Okay? So the first one, and I don't know if you can see it all the way over there on the left, but it says that this is an AB2 type of molecule. AB2 molecules have 1 central atom and 2 outer atoms and no lone pairs, because you'll notice there's not an E in that simplified formula, right? Because there are 3 atoms here, the furthest apart that the outer atoms can get from each other is being on opposite sides of the central atom in a straight line, which means their bond angle is going to be 180 degrees, and we are going to consider them a linear geometry. Now, you'll remember from the bell ringer that we talked about an AB molecule, which would just be one molecule bonded to another molecule. There's no central molecule, and they would also have linear geometry because the only way for them to be combined is on a straight bond. There's some nice examples here. An example of a linear bond would be BeF2, and you can see the Lewis structure drawn with the geometry described. The second type that we have is an AB3 type. So this would be 1 central atom with 3 atoms bonded to it. No lone pairs yet. The furthest away that those atoms can get from each other is by going to the corners of an equilateral triangle, which means that the bond angle between them will be 120 degrees. An example of this type of molecule would be BF3, where you have 1 boron atom in the middle and 3 fluorines surrounding it. So they want to get as far as possible from each other. The more atoms we add to this molecule, the closer they have to be, right? Because remember those attractive and repulsive forces that we talked about, right? But the VSEPR theory is saying those electrons that are in the bonds want to be as far as possible away from each other. So they go to the points of the equilateral triangle because if that puts them equal distances from each other, and that's as far as they can get away from each other, because maybe they could get farther from another bond by moving, but that would put them closer to the other bond, and so they want to get as far as possible from all other pairs that are there, which is why they take that triangle shape. We call it trigonal planar because they form a triangle, but all 4 of those atoms actually are in the same plane. So you could say they're all in the X plane, right? There's not a molecule that's moved up into the Y plane. So it's a triangle, trigonal, planar, all in the same plane. Now we're going to add our first lone pair of electrons. Okay. We have an AB2E molecule. So this is a molecule where there's a central atom, there are 2 outer atoms, and then there's a lone pair also involved. You'll notice that the lone pair is not drawn on this picture, and that's because while we consider the lone pairs in terms of repulsion forces, they are not bonds, so they are not part of the molecule's molecular geometry. But they're still there, and they're still going to apply forces to the atoms. So we only consider bonded atoms when we talk about the shape of a molecule, but where those lone pairs are still matters. So if I was going to draw the lone pair in, it would go up here. Okay, there'd be a lone pair of electrons there. And they are pushing down on those 2 bonded atoms. So the two pairs of bonded electrons and the pair of lone electrons are still in that triangle from the previous type. But since we only consider the atoms, it's a bent shape instead. And something we're going to learn about VSEPR theory is that, as we understand it, those lone pairs apply greater repulsion forces than the pairs that are in bonds. And as a result, they're going to push down on those two atoms and cause the bond angle between them to be slightly smaller. So in the previous one where we had 3 atoms, the angle was 120 degrees. In this one, it's slightly under 120. More like, I think it's like 117 or something like that. Okay. So a good example of this is O and F, where you have that nitrogen molecule in the center that has a lone pair off the top and then is bonded to an oxygen and to a fluorine. You'll notice that we've included a double bond here because in VSEPR theory we treat double, single, and triple bonds the same way when we're discussing molecular geometry. Okay, let's move on to the next set. So the next molecule we have is an AB4 molecule. An AB4 molecule has 1 central atom and 4 exterior atoms. So the farthest apart that they can get from each other is to form themselves into a shape that we call a tetrahedron in math. Okay? That's why this is called tetrahedral geometry. It looks like this in 3 dimensions. I have a nice little model here of it. This is the farthest apart those atoms can get from each other without being closer to another molecule. Okay? And if you measure these bond angles, you'll find that they are 109.5 degrees. Methane, that we talked about earlier, is a great example of an AB4 molecule. It has 1 carbon in the center and 4 hydrogens surrounding it. If we take the AB4 molecule and we replace one of the exterior atoms with a lone pair, we will wind up with our next type of geometry, which is an AB3E, and it is a trigonal pyramidal. So if you look at this, and now I'm covering up the atom on the top, assuming it's a lone pair, notice how this makes a sort of pyramid where the central atom is raised a little bit, but the base of the pyramid is a triangle. That's why this is trigonal triangle pyramidal. It's a pyramid with a triangle base to it. The bond angle for this is 107 because that lone pair that's on the top pushes a little more and deforms the 109.5 from the tetrahedral into a 107. And you can see NH3 on the side there as our example of this type of molecule. If we take the tetrahedral shape and we replace 2 of the lone pairs, or 2 of the atoms with lone pairs, we get our next shape, AB2E2. This is the same bent or angular shape as from above, but since there's 2 lone pairs instead of 1 lone pair, the bond angle is even smaller. So instead of being slightly less than 120, it's now slightly less than 109.5 because those 2 lone pairs exert stronger repulsion forces. Water is a great example of this type of molecule. The last 2 are a little bit more simple for us to understand because it's just adding 1 more molecule and then 2 more molecules to the central atom. So an AB5 is a central atom that has 5 around it. So you can take this tetrahedral shape that I have and add another 1 to the top. And those repulsive forces will push it so that these 3 that are around the center here, instead of being angled, will be flat in the plane. So what you wind up with is two pyramids that are connected on a triangular base, which is why it's trigonal, triangular, bipyramidal, bi meaning two, and then pyramids. Okay? The bond angle between the three atoms that make the triangular base is 120, just like trigonal planar. And then the bond angle between the two atoms that are pointed perpendicular to that plane is 90 degrees because they are perpendicular to the plane. So that means they're at 90 degrees. And then the last type that we will talk about is an AB6. You've added another molecule to this atom. So you have a central molecule with 6 bonded to it. And this takes the shape that we call octahedral. So instead of having two pyramids that have a triangle base, it's two pyramids that have a square base in the center. So all around, the angle between these bonds is 90 degrees.